Hi everybody, Professor Burns here. Let's take a look at section 2.5, which is called Special Integrating Factors. So make sure your cell phone is put away and you're paying attention and ready to take notes for the next couple of minutes. I've just got one example here and one new technique to show you. So suppose we have an equation that's in this format, but it's not an exact equation. So it looks like, it could be exact, but we take the partial of m with respect to y and the partial of n with respect to x, and we find that it's not exact. Well, what this technique does is it allows us to rewrite the equation by finding a special integrating factor that will make it into an exact equation. So here's the format that we're going to follow. First, we're going to find the partial of m with respect to y minus the partial of n with respect to x divided by the original n expression. And you might have to simplify and do a little algebra on that, but if that gives you a function, or an expression, I should say, that's strictly in terms of x, then we're going to use the integrating factor e raised to the integral of that expression with respect to x. If that doesn't work, try finding the partial of n with respect to x minus the partial of m with respect to y divided by the m expression. And if that gives you a function that's strictly in terms of y, then the integrating factor becomes e to the integral of that expression dy. Of course, if that doesn't work, then we'd have to find some other method. So let's do an example. And let's try this method. So we want to solve this differential equation. It looks to me like it could be an exact equation the way it's written. It is not linear. If we played around with it a little bit, we'd find that that y term, there's no way to get that y term by itself with a p of x function in front of it. So let's just check to see if it is an exact equation first. So always identify your m and your n expression. So m is going to start off as 2x squared plus y, and n is going to be x squared y minus x. So the partial of m with respect to y is just going to be the coefficient on that y, which is 1. The partial of n with respect to x is going to be 2xy minus 1. So clearly those don't equal each other, so this is not an exact equation. Let's go ahead and see if we can find that special integrating factor. And you could do either of these first, it does not matter. If you look at the expressions and if it seems like one would give you a better result than the other, you can try that one, but the order you do these in doesn't matter. I'm going to start with the top expression. So the partial of m with respect to y minus the partial of n with respect to x divided by n. All right, let's see what that gives us. So let's write that out. Partial of m minus the partial of n. Just kind of keep everything straight. The hardest part of these, I think, is just keeping straight what all your terms are. So this is going to be 1 minus, use parentheses here, 2xy minus 1 divided by the original n, which was x squared y minus x. So we got to do some simplification here and just see what this gives us. So we have 1 minus a negative 1. We get 2 minus 2xy over x squared y minus x. At first glance, this doesn't look like it does a whole lot for us, but notice that we can take a 2 out of the numerator, so that would be 1 minus xy remaining. And then in the denominator, we can actually take an x out, so that leaves me with xy minus 1. And hopefully you see these are opposite terms, 1 minus xy and xy minus 1. So those are going to divide out and leave me with a factor of negative 1. So this simplifies to negative 2 over x, which notice that is just a function in terms of x. And if that's the case, that's going to make my integrating factor. So it's going to be e to the integral of that expression. So let's go ahead and write that down. I'm going to put it over here. Mu of x then is going to be e to the integral of negative 2 over x dx. And that, of course, gives me e to the negative 2 natural log of x. And remember to always simplify that if you have a natural log in there. That's going to give me e to the natural log of x to the negative second which just leaves me with x to the negative second. So that's going to be my integrating factor. So let's take our original equation and we're going to multiply it through now by x to the negative second. So my new equation is going to become x to the negative second times 2x squared plus y dx plus x to the negative second times x squared y minus x dy equals 0. And as always, I would do simplification on this before you try to proceed. Notice that if I distribute the x to the negative second, the first term becomes 2 plus x to the negative second y. And the second term becomes, those x's go away, so I have y minus x to the negative first dy equals 0. Now just check and make sure that you didn't mess anything up by making sure this does give you an exact equation. M is now going to be 2 plus x to the negative second y. N is going to be y minus x to the negative first. So the partial of m with respect to y is going to be the coefficient here, which is x to the negative second. The partial of n with respect to x is going to be the derivative of this x term. So that's going to be, bring the negative 1 down, you're going to have positive x to the negative second. Hey, guess what? Those are the same. So now we have an exact equation. All right, let's go through the process of actually solving this using the method for solving exact equations. Remember how to start that out. We define f. F is the integral of your m function with respect to x plus g of y, which is to be determined later. So this becomes 2x, and then integrate that. Actually, let's see. Y is going to be your coefficient, so it's going to be y times the integral of x to the negative second, so that's going to be negative x to the negative first y plus g of y. And then remember, you take the partial of f with respect to y so that we can determine what that g of y term is. So that's going to be the coefficient on the y, which is negative x to the negative first plus g prime of y. And we're going to set that equal to our n expression, which is, notice what n is, back up here, it's y minus x to the negative first. Remember, that term has to match what's here. So I'm going to write it just so we can see the correlation a little better. Negative x to the negative first plus y. So that means that g prime of y is equal to just y. Let me write that a little neater here. Which means that g of y is equal to y squared over 2. Now go ahead and put it together. So my solution is going to be 2x minus x to the negative first y plus y squared over 2 equals c. So remember, f, the entire f expression, equals to your constant c, becomes your solution to your differential equation. And that's it. So we will definitely do some practice with this in class. I think on a test I would probably give you these formulas. You don't have to remember those because it is a lot to keep straight. But we do want to make sure we're comfortable with applying the method, and we'll work on it in class. So I'll see you tomorrow.